All right, for this video, we're going to cover content from both L9 and L10. So we're going to talk about steam and hydronic systems. So the first one we're going to be popping up here is the steam system. Um, right off the bat, BTUs, you're going to see that term a lot if you haven't already. BTU stands for British Thermal Unit. The reason why it's so important, well, first of all, it's the amount of heat required to raise temperature of 1 pound of water, 1 degree Fahrenheit. The reason why it's so important is because we measure a lot of things, both heating and cooling, with British thermal units. The next thing that we have to understand too is gauging pressure. So PSI versus PSIG. So when we talk about pounds per square inch versus pounds per square inch gauge, when we're dealing with mechanical systems, we are talking about PSIG. Because PSI is resulting pressure from 1 pound of force applied to 1 square inch. So that's more of talking about structural capability of something. When we're talking PSIG, we're talking relative pressure in relationship to the surrounding atmospheric pressure. So why it's so important when we're talking steam boilers is because if we have too much pressure, obviously we can either collapse a tank or we can explode a tank. So we want to make sure that our PSIG is intact. A couple other things leading in here, boiler classification determination. So we basically have 4 things you need to look into. Is it steam or hot water? For the sake of this PowerPoint, we're going to talk mostly steam. Is it electric or combustion? Again, for this one, we're talking combustion. And if so, what type of fuel is that combustion boiler burning? What pressure is it operating at? That determines if it's a high or low pressure system. And then what type of design is it? So we're going to kind of bypass the first couple because we're talking steam and combustion. But when we get into classifications of pressure, if we have low pressure, somewhere in 15 psig or below, we're talking low pressure systems, and anything above that 15 psig is a high pressure or power steam type of system. Low power systems used mostly for just space heating, but our power steam is used for a lot of processes, so industrial plants, power generation applications, anything like that. Large industrial and commercial applications will be using power steam. Within any other of the systems that we talk about, there are general heating process, right? There's 4 steps. We have to generate the heat, we have to distribute the heat, we have to use it, and then we're also talking about recovery too, because we don't want to waste the heat within our systems. It's also important to note that there's definitely a lot of ways we can design systems, and all these steps may have a lot of different variables, right? Like, so what type of equipment we're using, what the end use functions, all that stuff. So moving along here, the steam system has a few generic processes right from the get-go. So the boiler is the piece of equipment, obviously, that you're heating up the water and you are creating the steam with. The next piece in the puzzle is the steam header. Also, a lot of people call it a manifold. That's basically a large distribution supply branch system where all the steam comes in and then it's distributed to different branch lines to get to your heating units, which is the 3rd step. This is where we actually transfer that heat that's generated by the steam into whatever that end use function might be. After that, once we give off that steam and the system starts losing heat, next step is the steam in there starts to condensate. So we need to collect the steam and the condensate at the traps, discharging different non-condensable gases to exhaust from the system, and then collect the condensate and keep the steam trapped in for efficiency purposes and safety. The condensate tank is the next piece of the puzzle in your generic steam system, and that's where we store any kind of condensate that is collected from your system and is refed back in. So here is your generic process, right? We have the boiler, we have the steam header or manifold up here, we have the branches that go to the different units, we have a heating unit that transfers the heat, right? The steam trap collects the non-condensable gases and expels those from the system, collects the condensate, sends those to the condensate tank, and traps the steam inside to maintain heat and balance within the system. After the condensate tank, we have feed water system that pushes it back into the boiler. So when it comes to the boiler design, your boiler is your primary heat exchanger to create the steam. We have 2 different typical types. We have fire tube boiler or a water tube boiler. I'll get into that in a second here. The heat exchanger process, right? We have to deal with moving heat from one object to another. Generally, we're talking two fluids. Sometimes it could be a solid or a fluid. Once you get into different mechanisms like air conditioning, we talk about air once in a while as well, being one of the fluids. Um, but that transfer prevents overheating. It removes heat for refrigeration. It provides space heating in radiators. It does more than that too. Just a couple generic things for heat exchange. So here's your generic heat exchanger, a shell and tube heat exchanger. We have one fluid in the shell side that's coming in here, going around some baffles, coming out the shell side here. And then we have a tube side fluid coming in, going this way. And this is where the exchange happens. One of these is going to be hot, one of these is going to be cold, right? So it's either the shell or the tube. So a fire tube would obviously have the firebox creating the heat within the combustion gas would be inside the tubes. That's boiling the water that's in the shell. So the fire tubes heat up the water, the steam pops out the top, and any of the heat, all the combustion gases that are going through the fire tubes are getting exhausted out the flue gas. So the feed water's coming in the bottom here, steam's going out the top. In a water tube boiler, it's the opposite, where we have a firebox that the water system is going through the tubes. So in this one, this is a high efficiency one where we would have the feed water coming in to the drum here, and then going into our fuel burning chamber. Once that water is boiled and it's producing steam, it's captured up in this steam drum. From that point on, the steam drum collects anything that's exceeding its capacity and getting redistributed back into the fuel chamber for additional heating or superheating. So once that superheated steam comes out, then we have that going back into our system for the heating process. So this is more of a energy efficiency type model where we're collecting the heat twice. And then it's very common in large process plants to have combination fire and water tube boilers. So you can see here all the different parts and pieces are shown, but one side is your water tube, one side is your fire tube. Different type of heat exchanger that's commonly used in a lot of systems, not really within the steam itself, but a plate heat exchanger is used for connecting your boilers and your steam system to other heating components a lot of times. So just another way, and I have a video here that explains better how the plate heat exchanger works, but basically you have cold in one side, hot in the other side, and across the plates here, it creates the exchange mechanism. So we're taking the hot from inside the one and pulling it out the other side and exchanging it across the plates. Now we're going to start going through the different components. Also, beyond the initial heat exchanger, we have the condensate return tank, which is obviously where at the very end of your process, you're collecting the rest of the condensate. You keep it in a receiver tank. We have an overflow seal just to make sure that we have balance within the system. If we have too much, the pressure is off. That's a problem, so we want to make sure that we vent anything out as far as that goes. And we also want to make sure that if there's any overflow, we get rid of that as well. We generally connect this condensate return tank into our feed water system, and this is what supplies the boiler and maintains the quantity in the system, the pressure and the temperature within the boiler. Typically what we're doing with feed water is we're combining that condensate tank water with fresh water that's coming back into your facility. And this is just another diagram showing kind of how the boiler feed water comes to be. So you guys can take a look at that as well. Another piece of the puzzle is the economizer, which I didn't really mention in your generic system, but this is more for energy efficiency purposes. Just like you saw in the forced air one, we have ERVs, or energy recovery ventilators. This is the same process. So what we're doing here is we're capturing heat that would otherwise be lost from our boiler, and we're preheating water that's coming into our boiler. So the way that would work is instead of the feed water tanks sending the water right into the boiler, it's going to bypass the boiler, go up into the flue where it's going to collect all the heat that's getting exhausted out. It's going to start preheating that water so the feed water line comes into the boiler already hot, so the boiler doesn't have to do as much work. Another energy efficiency thing and one to help the system is a deaerator. This removes oxygen and carbon dioxide, any other dissolved gases from the feed water system. Those dissolved gases, whoops, sorry, can cause corrosion. It also helps raise the feed water temperature for higher efficiency. So that's what your de-aerator does, and that's at the very end of your system as well down here, as you can see in a high efficiency industrial steam system. So we have our boiler that's getting fed from our feed water, but that's going into our economizer first, right? And that economizer is pushing it back into the boiler, so we're preheating the water coming in. Then it goes to your end use. We have our steam traps after that. We have our condensate receiver tank and our pumps that go into our de-aerator, which again, taking out the carbon dioxide and oxygen, raising the temperature a bit, sending into our feed water to raise the temperature even more and restart the cycle. I'll let you guys take a look at this on your own, but this is just another sort of graphic. I think on the one you guys can download, it has a little more explanation on it. Now getting into the boiler accessories, I'm going to shorten this one up a little bit for you. I'm going to let you guys go through this. We're talking traps, we're talking how they work. We have a video here to show how that works as well if you'd like to see more. But traps are extremely important for the system. They create the efficiency, right, because we're keeping steam in there. They're also maintaining safety. We're keeping the condensate moving. We're exhausting, or we're venting out any kind of non-condensable gases. But here we go. I'll let you guys get through the rest of this. We're just talking safety valves, different types of valves within your system, different types of gauges. So I'll let you go through all of these on your own. Blow down valves, gauge glass, and vacuum breakers as well. Vacuum breakers are quite important for safety purposes. When the boiler is shut down, that steam is in its condensing, and that forms a vacuum in there. So we have to maintain that pressure differential inside and outside of the boilers, or else we could crush the boilers pretty badly. And then terminal devices or thermal devices or heating units, right? Typical radiators, convection baseboard, in-floor heating is also one of them. Last piece, just talking about the three modes of heat transfer, whether it's conduction, convection, radiation, just kind of a reminder for you as well. So yeah, you guys can finish up those slides on your own. I want to pull up this one as well, just talking about really quickly the hydronic systems here. Let's see. And this one's a really short slide. It's only 10 slides, just showing how the different loops work in hydronic systems. What we're doing here, so after once we're heating in the facility, we're taking whatever that hydronic material is, primarily water in most cases, to go through our radiators or convectors. So what we're doing with the hydronic system is we're circulating hot or chilled water through the space to heat the space or cool the space. Normally, when we're in commercial applications or larger facilities, we might be using different types of refrigerant for that because they boil at different temperatures, so they can be a lot more efficient. But in residential applications, we generally use water. And then technically steam is a type of hydronic system as well, but steam is normally the larger process plant that's producing a lot of the steam to send out to other facilities. So right off the bat, we have a series loop. So this is the most basic, most commonly used in residential. It's also the most inexpensive and most inefficient. So we have a boiler here that as we're sending that hot water out, it's going into your different baseboards, right, at each one of these different convectors. We're transferring that heat into the space, so we're losing heat and we're dropping it all throughout the system. So this last one has to work a little bit harder or call for more heat to maintain heat within that space. A single pipe main is basically the same thing, except for we branch out for the different thermal units. So that temperature drop occurs, but maintains that individual flow rate better than a series loop. So we can shut off different units within this one, and we can maintain the main line going all the way around. And we can maintain the balance for the heat distribution a lot better with this process as well, because the heat is bypassing as well as going to the different thermal units. Two pipe systems is where we start getting into both supply and return, much more for larger applications. Sorry, jumped ahead a little bit here. And we have two different types of two pipe systems. We have direct return or reverse return. So the direct return is, sorry, I had the animations a little bit off there. The return line provides the shortest path back to the boiler. It's the most direct path. So the first unit supplied is the first unit returned. So what that means is we have our hot water generator, right? That's pushing the heat out this way. And then once it goes to that thermal unit, it comes back from the supply directly back to the generator, right? So every time it branches off to the terminal unit, it returns the heat back in to restart the process. Okay, so the first unit supplied is the first unit returned. In a reverse return, looks like I got my animations wrong on this one too. Right, we're doing the opposite, where the first one that is supplied is actually the last one that's returned into the unit. Okay, so that first one comes in this way, and then the supply line, or the return line, sorry, follows right along in parallel with you with the heat throughout the system. So it helps actually control a lot more of the balance within of the supply and return, and it helps maintain the heat a little bit better. Plus, there's a little bit less piping, as you can see. Now you can also get in 3-pipe systems too. This is where we have more 2 supply, 1 return. Okay, used where heating and cooling is required for different parts of the units, right? We have 4-pipe systems where we're basically separating heating and cooling, right? So we have return and supply for both heating and cooling in that system. So we're basically talking a two-pipe system at that point. And that's pretty much all I want to talk about there. We use hot water more for smaller applications within our facilities. So a lot of times we're talking hot water boilers within individual buildings, but we do use a lot of steam for process stuff, industrial stuff. Universities still have a lot of steam plants that are pushing steam to help heat many buildings, if not all of the buildings on campus. So normally for different applications, but same general process. And I'll let you guys look through the rest of it. A lot of times, what I run into in different cities is they used to have a lot of steam processes that they're sort of switching off of to allow for individual facilities to have their own, hot water boiler systems. But with that, I'll leave you to it, and I'll see you for the next one.